Our next speaker is Sophia Lu. If you want to come up to the stage. So Sophia is a PhD student in the statistics department.
Thank you so much, Laura, for the introduction, and I'm very excited to be here. My name is Sophia. I'm also the only thing between you and lunch. Today, I will be talking about towards faithful synthetic data generation via the Penalized Optimal Transport Network. And I want to begin by recapitulating the concept of synthetic data. Synthetic data is artificially generated data that mimics real-world data sets without making prior assumptions. And you may wonder, without making prior assumptions, this sounds too good to be true, so how is this done? Well, the core idea is to use complicated, capable machine learning models to learn the data generating distribution. So a pipeline might look something like this. Nature gives us some real data, which we collect to train machine learning model that outputs some synthetic data. We can either then combine the synthetic data with the real-world data for augmentation purposes, or we can use it to perform downstream analyses such as clustering and model selection. A very popular family of generative models is called the Wasserstein Generative Adversarial Network, which we will abbreviate as Wasserstein-Gens henceforth. So in Wasserstein-Gens, it consists of a generator network and a discriminator network, and they're trained in a dynamic fashion. So the generator network takes as input a low-dimensional random noise vector, usually sampled from the Gaussian distribution. It pushes the random noise through a sequence of network layers and then outputting a fake batch of samples. So here, the fake batch of samples happen to be a fake A that actually looks quite realistic. But how do we evaluate whether this generated sample is good or bad? Well, we have something called the discriminator network. The discriminator takes as input the training set, meaning the real data, and then also the synthetic data, and outputs a score that distinguishes the real data from the fake data. So using this score, we can approximate something called the one-Wasserstein distance, which is defined as the minimum transport cost necessary to move probability mass from the generative distribution, so the synthetic distribution, to the real data distribution. With the approximate one-Wasserstein distance, we can then perform backpropagation with respect to the generator and discriminator. Okay, so that's the framework of Wasserstein-Gens. But the caveat is that Wasserstein-Gens are notoriously difficult to train in practice. And this is primarily due to two reasons. So one is due to the adversarial formulation, because we have a zero-sum game between the generator network and the discriminator network. So what this means is that it leads to unstable training dynamics. The second cause is due to something called the curse of dimensionality, and this refers to the fact that the Wasserstein distance is inherently unstable in high dimensions. So together with these two causes, Wasserstein-Gens frequently exhibits this undesirable and pathological behavior called mode collapse, which is the phenomenon that the generator only produces a limited subset of outputs, hence the generator collapses to the mode, and this leads to reduced diversity of generated samples. And we have a cartoon example demonstrating the unwanted effects of mode collapse. So here's my observed data. It has two groups of people. We have a majority group with the arms down people, and we have a minority group with the arms up people. Now, in synthetic data with mode collapse, it might give me only samples from the majority group, meaning the arms down people. And what this means is that I have completely lost access to the minority group if I had performed analysis using only the synthetic data with mode collapse. So this can lead to serious consequences as expected for downstream analyses and might even undermine the validity of the conclusions drawn from the synthetic data. Mode collapse is actually a terminology used quite generally in the literature, but we classify mode collapse into two types in our work. We recall type 1 mode collapse as mode dropping, which happens when the generator fails to assign adequate weights to the clusters. So here in the images, you can see that in the true data, I have 3 clusters, although I have a big cluster and 2 smaller clusters. And in Wasserstein-Gens, the smaller clusters aren't captured adequately, hence that's why you don't see the contours for the smaller clusters. And practically, this means that it could result in significant misrepresentation of subgroups in heterogeneous populations. And this could have serious consequences for algorithmic fairness if I use the algorithm to score individuals for employment, for insurance, etc. And type 2 mode collapse is what we call support shrinkage. And this happens when the generator fails to adequately capture the tail behavior and extreme outliers. So in the example here, we have orange demonstrating the synthetic sample, and turquoise being the real data. You will see that if you stare at the left and right tails of the image closely, you will see that the orange actually doesn't place any mass there. And practically, this means that my synthetic data omits important extremal information. And usually, across disciplines, these extremal tail information are of specific interest. So for example, in econometrics, the upper and lower tails of my income distribution are of specific interest to policymakers. The takeaway message is that if we don't regularize in the right way, our model will be prone to mode collapse. And our work addresses this unwanted behavior. So recall that Wasserstein-GANs are difficult to train for two reasons: the adversarial formulation and cursive dimensionality. Well, let's tackle them one by one. To remove the unwanted effects from the adversarial framework, well, we can remove the discriminator network and hence eliminate the two-component formulation. To mitigate the cursive dimensionality, well, we can incorporate penalties for mismatch along each univariate marginal distributions because they're very low dimensional. So this was the structure of the GAN formulation. First, we eliminate the discriminator network. And we can do so by using the Monch-Kontorovich primal formulation as opposed to using the dual formulation employed by Wasserstein-GANs. Then we introduce something called the marginally-penalized Wasserstein distance, which leverage marginal penalty as a form of regularization in order to guide the alignment of my joint distributions. Now, the advantage of that is we can actually perform exact primal evaluation. So in addition to the marginal alignment, we can perform exact primal evaluation using an optimal transport solver. And we perform one-step backpropagation as opposed to doing backpropagations with respect to both generator and discriminator networks. So theoretically, we were able to establish guarantees for this for POTNet. So we have a generalization bound, we have convergence rates. We showed that POTNet provably mitigates type 1 mode collapse, which is mode dropping. We also showed that POTNet mitigates type 2 mode collapse, which is support shrinkage. Now let me show you empirical evidence trying to convince you that POTNet actually does mitigate mode collapse. So first, for type 1 mode dropping, on the left-hand side, I have the real data, and then I'm showing three models. So POTNet is our model. Wasserstein-GAN is the Wasserstein-GAN implemented with gradient penalty. And then the last model, OT, is the same network structure as POTNet, but without employing the marginal penalty. And you see that in both Wasserstein-GAN and the model without marginal penalty, it exhibits type 1 mode class because it doesn't have the small contours corresponding to the minority clusters, meaning it didn't assign adequate weights to the minority clusters. Now for support shrinkage, the setup here is a conventional likelihood-free inference setup. And in the first panel, again, I have the ground truth data. Second column corresponds to POTNet. Third column corresponds to Wasserstein-GAN, and then fourth column corresponds to same network structure without gradient penalty, without marginal penalty. First, I want to just sort of highlight the remarkable resemblance between the contours corresponding to POTNet, the synthetic data, and then also corresponding to the real data. Now, if I put blue lines around the support of the true data, you will see that without adding marginal penalty, I actually shrink it horizontally, so I am losing tail information. I can also illustrate this in three-dimensional space. So support shrinkage in 3 dimensions looks like this, where my generated samples live in a thin hyperplane for each cluster, as opposed to sort of that voluminous shape in the original data. Now for the real data examples. So we can compare POTNet against a very widely used alternative called CTGAN, which is for tabular data generation. And if you look at the contours, I would say that the contours corresponding to the real data versus the synthetic data are almost indistinguishable unless you look at it with a magnifying glass. But for CTGAN, it fails to capture that sort of symmetric composition of the first mode in terms of the longitude. I can also use POTNet to generate synthetic digits. So this example is trained on MNIST handwritten digit dataset, and I compared POTNet to Wasserstein GAN. So looking at the generated digits by POTNet, you see that the digits are clear and they are discernible. But for Wasserstein GAN, I've put red boxes around the digits that didn't really look discernible, and they look maybe like a combination of 2 digits or 3 digits. In terms of sampling generation, POTNet is extremely efficient. Compared to the alternative CTGAN, it's actually 80 times faster. And although this is not 1,000 times faster, but if you look at the generation time, it's 667 microseconds to generate 3,000 samples, 3,000 samples, which is very fast and very efficient if you need to generate massive data sets. So I want to conclude by talking briefly about why does high-quality synthetic data matter? Or how can you use POTNet? Well, you can use it for 3 purposes: augmentation, evaluation, and privatization. So for augmentation, you can use POTNet to generate synthetic data to mitigate class imbalance or for rare event simulation. So you would supplement your training data with synthetic samples from the underrepresented groups or from the rare events. For evaluation, you can also use synthetic data generated by POTNet to guide the model selection process or to systematically evaluate method or model performance using these very faithful, realistic data. The last purpose you can use it for is privatization, and this is actually future work. But the hope would be that you can generate statistically similar but non-identifiable data sets so that they don't compromise individual privacy when you need to release data. So for example, if I have medical records of individuals, I cannot share them because they contain personal information. But if I generate synthetic data sets that capture the structure of the data set without compromising individual information, then that could be very promising in terms of data sharing. So I want to thank my wonderful collaborators, my advisor, Professor Wenheng Wang and Professor Chen Yangzhong. And also, if you would like to use POTNet, please scan the QR code here. I'm happy to take any questions now.
I just want to compliment you first on a really, really beautiful talk, well explained. And some of this stuff I've been trying to get my head around for a while. But the question, so can you recognize sort of empirically when you've had this mode collapse?
Mm-hmm. Yes.
Can you do that?
Thank you so much for your kind words. And also, yes, we can recognize when we have mode collapse. So let me maybe show this example because I think it's a very good illustration. So here we see mode collapse because in the orange data, you see the piling up of the mass at the modes, but then you see the shrinkage of tails. I would say this is a canonical mode collapse behavior, which in short, you lose the variation in your samples.
If you have a highly multidimensional space,
Mm-hmm.
how would you recognize that?
Yes. So in a highly multidimensional space, visual analysis would be more difficult because we can only visualize 3-dimensional space. So some people visualize along each marginal. If we have mode collapse in marginal distributions, then that would imply mode collapse in the joint distributions. There are other metrics for measuring that, so we can analyze the variance, so we can go up the moments ladder and use metrics to analyze, to quantify mode collapse.
Thank you so much for this presentation, very useful. As a future user, I'm interested to know how this model is distributed. Is it open source, or also what are the processing requirements?
Mm-hmm. Thank you so much for your question. So this model is open source. It's on GitHub. You need to install PyTorch, and also a library called POT, but all the requirements are listed on GitHub. And feel free to start like a thread if you reach any installation issues.
Obviously, the way that you built this model was to remove the part of the discriminator that says whether it is true data or fake data. At least from the example images you provided, it seems that even though you remove that explicitly from the model, it still produces images that looks like real images. Do you have numbers on, was there any reduction in performance in the discrimination between real and fake?
Yes. So that's a great question. And let me briefly talk about why the removal shouldn't actually cause any problems, but it actually would increase the accuracy, so to speak, in the distance evaluation. So in Wasserstein-Ganz, the discriminator network seeks to approximate the one Wasserstein distance, and it can do so by outputting a score. But now we have an exact distance evaluation using the optimal transport solver. So previously, it was an approximate distance, an approximated value. Now we actually have the exact value. So we don't lose any of the capabilities. We actually improve upon the approximation.
Interesting. And a follow-up, if I may, do you find that the accuracy in discriminating true and fake is the same of whether you're in a overrepresented class or an underrepresented class? Does that question make sense?
Yes. So I don't think they are the same. And I think that's actually one of the causes to this unstable behavior, because you can't, like, the capability of the Wasserstein-Ganz depends on how capable the generator is relative to the discriminator. And if we make one of them too capable relative to the other, then we don't get convergence, usually. So that's why I would presume that I think it's very likely that there are differences between these two representations.
Great presentation. Can we use this framework to generate time series data? Maintain that order structure in your real data set?
That's a great question. Yes. So the question is, can we use POTNet to generate time series data or data with some sort of dependence? And that's a great question. So we're actually exploring using POTNet to generate panel data, which is like a form of time series data. Currently, we don't have any guarantees that it will work, but it might.